history here. We had 392 people register, a few more in the meantime. The majority, slight majority, are students, looking at where people come from, Stanford and Berkeley, a lot of industry, and we have some people from academia around the Bay Area as well, not just Stanford and Berkeley. I'd like to take this moment to thank all of our sponsors who made this event possible, including the cookies and the coffee and so on. So thank you to all the sponsors, CPAR, Zoox, Bosch, Anki, Intuitive Surgical, Skydio, and TRI. Thank you. As for the people who organized this, technically it's me and Marco, but who it really is Ron Bernstein. So thank you, Ron, for doing all this amazing work. And we'll thank him once more at the end, but thank you, Ron. Our schedule for today, we're going to have a lot of faculty talk, about 23. We're going to have student spotlights. I'll take this opportunity to ask the student presenters to make sure that they have their posters set up in the common area is really what it's called. You exit, you go through the corridor, and you find a big common area. There you find poster boards and easels. So what we're going to do is we're going to have everyone in both sessions, both the early session and the afternoon session, go ahead and set up their posters. It's your choice whether you want to be presenting your poster also in the kind of other coffee break. That's okay. The posters are going to be tagged for everyone to see with this is a morning poster versus this is an afternoon poster, so that all of us, when we go and walk around, can actually figure out whether we should expect the person to be there or not. So if you're in the morning session, pick a morning poster board. If you're in the afternoon session, pick an afternoon poster board. And with that, let's get the ball rolling. It is my pleasure to introduce our first speaker, Peter Abil from UC Berkeley.
Good morning, everyone. Can everybody hear me in the back? That's good. Thanks. So a lot of the work in my lab is on how to make robots learn. And I thought I'd give you a quick update on what we've been up to since last year's BARS, and then dive into a little more detail on a few of these projects. So the themes that we've been working on, a big one is kind of improving the core of deep reinforcement learning algorithms, making them more sample efficient, introducing better exploration methods, and also extracting more signal out of existing rollouts. Another big theme has been transfer, how to leverage what you experience in one environment to be more effective in another environment. Another one is hierarchical learning. Often in reinforcement learning, everything's happening at the same time scale, which makes it very difficult to act over long horizons. And a big challenge is how to introduce some kind of abstractions into that so you can act over maybe a day-long time scale rather than just 100 seconds or something. A lot of work has been on learning to learn. The idea here is that rather than having humans design what the learning algorithm should be, learn the learning algorithm itself and learn it prior over possible situations you might encounter so that this learning algorithm can take advantage of that. I'll say a little more about that later. Another big theme has been how to learn to communicate and how to have many agents interact in a single environment and cooperation or competition settings. A big challenge that I think remains ahead of us is to try to crack model-based RL, in that right now model-based RL methods tend to saturate at a level of performance below what model-free methods can achieve. But the hope is that model-based RL could be more sample efficient, but then it's not great to be more sample efficient yet have worse performance, which is the current state of affairs. Some other things we've been looking at is how to automatically generate curriculums. When we go to school, we don't right away go to college. We go to elementary school first, and then we go to middle school, high school, then college, and there's a whole progression of things you learn. That's so that we can learn more easily. How can you generate those curricula automatically? And then also quite a bit of work on how to make AI human compatible and safe, imitate, and how to scale up. Now let me tell a little bit about the key ideas behind 3 of these. First one is imitation learning. there are two big challenges that people traditionally encounter in imitation learning. One is the fact that real imitation would learn from a third-person point of view. You would just download a YouTube video, and that'd be enough to understand what to do. There's an extra challenge there then that typically the YouTube video will not be a video of your robot doing the task. It'll be some other incarnation, maybe a human doing the task. And so you have a mismatch between your robot and what it's seeing. These are very exciting challenges to take on. We decided to just completely sidestep them and set up a virtual reality-based setup where we have the human demonstrate controlling VR controllers. So here Tianhao Zhang is moving the robot around, puppeteering it by holding a standard HTC Vive controller. Makes it almost trivial for anybody, not just PhD students, to control a robot and teach it new skills. And what I mean with teaching new skills is that it turns out if you get your data this way, which is very high quality data with very high signal because there's completely perfect match between how you teach and how the robot's supposed to do things on its own, then you get learning in less than 30 minutes per task. And you can vary the environment. The robot is using the raw pixels that we're seeing here. We're seeing it from the robot's point of view and processes from raw pixels all the way to motor commands. Now, sometimes you still do want to learn in simulation because you can collect a lot more data in simulation more easily than you can in the real world. It's more scalable, it's less dangerous, and it's easy to get labels. If you collect data in simulation, the labels are there because the simulator knows everything that's in there, it's generating it. But then the question becomes what you learn in simulation, how to apply it in the real world. Often if you train something in simulation and then test it on a real robot, it's not going to work. One solution to that is to make really realistic simulators, and especially in the context of driving, people are getting pretty close to things that look almost like the real world. A few downsides is that it's actually very hard to build such simulators, and often those simulators are not very fast. And so it might still be a slow data collection process, even in simulation, if you have very high fidelity simulation. Another line of work, Trevor Darrell here at Berkeley has pioneered a lot of that, is to somehow learn pairwise. You have a simulator, a real world, and you learn in both at the same time and learn the mapping between the two explicitly, such that when you learn something in simulation, you can transfer easily to the real world later, or at least that's the hope. So what we've been looking at is this hypothesis that maybe if you generate enough variation in the simulator, even if none of it is realistic, for example, on the left here, none of the rendered images are realistic images compared to what's real, which is on the right. But if you introduce enough variation, maybe you can still capture the essence of what you want to learn and generalize to the real world. Turns out that's possible. You can learn just from simulation to recognize where an object of interest is. And in fact, you don't even need pre-training. So with zero training data from ImageNet or any other real-world source, you can reliably train these neural nets. This was inspired a lot by prior work by Fereshteh and Sergey Levin on doing something very similar for learning to fly. They looked at, can you train a quadcopter fully in simulation to fly down hallways without ever seeing any real-world environment? And sure enough, they could deploy it in the real world without any training in the real world. We've also been looking at that in the context of dynamics randomization. So what I mentioned so far is training a computer vision system with just simulation. But how about the dynamics? A real fetch robot, a simulated fetch robot. Maybe you can randomize damping, mass, friction, damping of the object between table, height, and so forth. And maybe train up a deep neural net, recurrent neural net, to be able to deal with that kind of variation by just training in simulation, still get it to work in the real world. Here's an example. Pushing objects around is something that is very hard to simulate reliably, but what we see here is a policy that was trained only in simulation, yet is capable of reliably controlling objects in the real world and push them to their destination. The last one I wanted to give a quick highlight about is learning to learn. How do we formalize learning to reinforcement learn? The way we look at that is, say, instead of trying to train a control policy, we tried to train a reinforcement learning agent. So we want some piece of code that, if deployed in a new environment, a new MDP-M, and gets to run for a few trajectories, a few episodes, over those few episodes can learn to perform well. So we want to somehow find the parameterization of that agent such that we maximize expected reward over, let's say, capital K rollouts in an environment the agent has never been in before. So that's the optimization problem we want to solve. Of course, the big question is how do you parameterize this agent so that you can optimize it and that it does well in new environments? Last year I talked in bars about RL squared, which is a big recurrent neural net parameterization. We've also done some work since on something called MAML. This is together with Chelsea Finn and Sergey Levin. Most recent incarnation we've been looking at and that outperforms both of those is something called Simple Neural Attentive Meta-Learner. It's a lot like RL squared in that it just takes in all past data and then based on that decides what to do now. But rather than using a recurrent neural net, it's based on ideas from WaveNet using dilated temporal convolutions and then combined with attention to be able to also see the detail in the past, not just a dilated version of the past. We tested this on bandits where it outperforms the prior methods, including human-designed methods that took humans many years to design. It outperforms prior method on small MDPs, again also human methods as well as RL squared and MAML. It outperforms them on robotic control tasks, Ant and Cheetah. Outperforms them on navigation. This is a setting where you get raw pixels and the robot has to learn from raw pixels to navigate a maze it's never been in before and reliably essentially build a map, even though we don't give it any kind of map explicitly, it builds it up in its internal memory to then be able to navigate reliably to the destination. It also happens to work well for classification, which was not our goal, but it outperforms the state-of-the-art in dedicated methods that learn to classify, both on OmniGlot and on ImageNet. Still pretty good, but actually still a big challenge remains, that is to act over very long horizons. And learning to act over long horizons, we have tried to tackle a little bit, but a very long way to go still by explicitly building in a little bit of hierarchy. So the architecture we're looking at here is something where we do the same thing. We train an agent to be good at adapting to new environments. We explicitly tell the agent that there is two parameter vectors, theta and phi. Theta controls a policy that can only make decisions every 100 time steps. And the decision made by theta is which of the other low-level policies to currently execute on. And then the low-level policies make decisions every time step. Here's an example of the result in action. We trained a simulated ant robot in a variety of mazes. It, on its own, discovered 3 low-level policies that are useful if in the future it gets deployed in new mazes so that it can quickly adapt to discovering what's in those new mazes and navigate towards a goal. And in fact, here what we see is there's a big enemy sitting there at the top. We shall bounce it. But it turns out it takes advantage of that because the destination is at the bottom and the knock by the enemy is actually beneficial to get to the goal much more quickly. Here's a summary of the work that I highlighted. Thank you.
Next up is Marco Pavone from Stanford.
Okay, good morning, everyone. Deploying autonomous robots in our society forces us to reason on the concept of risk and safety. So in this talk, I will give you an overview of our work toward infusing risk sensitivity in decision-making under uncertainty. Broadly speaking, risk sensitivity refers to an increased sensitivity to events of small probability and high detrimental consequences. For example, considering an application from my work on space robotics, a robot hopping on an asteroid should be able to account for events of small probability, like, for example, falling in a pit, which, however, could spell the end of the mission, as it happened for the Rosetta mission from the European Space Agency. However, agreeing upon methods to promote risk sensitivity is a contentious topic. A natural approach, and indeed the approach advocated in my work, is to consider a Markov decision process formulation and replace the standard risk-neutral expectation with a risk measure. But then the question is, how do we choose such a risk measure? Common choices are represented by worst-case risk models, where we select the worst possible outcome. This corresponds to extreme pessimism. Mean risk models, whereby one additively combines the expected value of a random cost with a measure of its uncertainty, for example, its variance, or the expected utility approach, where one measure risk by taking expectation of a disutility function of a random cost, where the disutility function is a convex increasing function that models the psychological evaluation of a cost. Perhaps surprisingly, most common approaches lead to paradoxical results. For example, consider a mean risk model, consider a very simple setup whereby we have 4 possible outcomes, omega 1, omega 2, omega 3, omega 4, and 2 cost profiles, z and z prime. Since z is less than z prime in all possible states of the world, and any sensible decision maker would prefer z to z prime, since z is the cost and we want to minimize cost. Yet a decision maker that is using a risk-sensitive model would prefer z prime, which represents a paradox. And there is nothing pathological with this example. Similar pitfalls would arise with other types of risk measures, for example, those that are based on expected utility theory. The key point here is that devising a sound theory of risk-sensitive decision-making requires us to carefully reason about models to ensure rational risk assessments, in particular to avoid paradoxical results. To ensure rationality of risk assessments, there has been a major shift in risk theory in the past decade toward an axiomatic definition of risk measures, whereby one specifies a list of axioms that any rational risk measure should satisfy. With this idea in mind, we have studied axioms that the risk measures used in robotic application should have. An example of axiom is represented by monotonicity, which stipulates that if a random cost z is less than z prime in all possible states of the world, this is an inequality between random variables, then the risk of z should be less than risk of z prime. This immediately rules out the paradoxical result related to mean variance risk model. Details of an axiomatic framework relevant to robotic applications is provided in a recent paper that I published with a former postdoc in my group, Ani Majumdar. Here we just mentioned that a prominent class of risk measures that are axiomatically justified and hence by design avoid paradoxical results is represented by coherent risk measures. Coherent risk measures enjoy a powerful representation theorem. In particular, any coherent risk measures can be represented as the expectation with respect to a worst-case probability distribution, where that probability distribution is chosen adversarially from a convex set of probability distribution P. P is essentially a subset of the probability simplex and uniquely identify your posture toward risk. If P, this subset, corresponds to the entire risk envelope, then we recover a worst-case risk model. Now, an important consequence of this result is that the risk can be assessed by solving a convex optimization problem, which allows the derivation of fairly efficient risk-sensitive decision-making algorithm. Well, this is satisfying from an algorithmic modeling standpoint. We want to dig deeper into the conceptual importance of considering a risk-sensitive objective. Specifically, I want to better understand the relation between risk sensitivity, that is robustness toward uncertainty, and the policy robustness, that is robustness toward modeling uncertainty. To do so, let's consider a model whereby we perturb our nominal transition probability with the perturbation factors delta that model uncertainty in our model. And let's assume that the uncertainty is budget, meaning that the product of these perturbation parameters is upper bounded by a parameter eta. And finally, as a cost function, let's consider a conditional value at risk cost function, which essentially corresponds to the loss in the tail of a distribution. In particular, conditional value at risk at alpha is the expected loss in the worst alpha % of cases. Then one can show the fairly enlightening results whereby minimizing a conditional value at risk objective corresponds to solving a robust MDP with respect to unknown transition dynamics, where there is a budget with respect to the uncertainty in those dynamics. In other ways, minimizing a risk-sensitive cost corresponds to promoting robustness of a policy towards modeling errors. And we're quite excited about these results because it provides a unified way of reasoning in terms of robustness to stochasticity and robustness to modeling errors. That is a pathway toward a unified view of uncertainty. I believe this class of risk models and algorithms open the avenue for a number of new research directions. For example, theoretical foundations, how to ensure assessments, rational assessments of risk through time, application of axiomatically justified risk-sensitive models to control, for example, model predictive control, to reinforcement learning, inverse reinforcement learning, principal ways of transferring in a safe, aware manner policy learned in simulation to the real world, similar to what Peter was discussing before, and more in general techniques to enable safe exploration of new actions in the context of robot learning. And applications to both robotic applications, robotic context. For example, I've been using these algorithms to the problem of entry, descent, and landing for Martian probes together with JPL. I've been using these models to the problem of robot navigation on asteroids and comets, and also to self-driving. But here in the final 3 minutes, I want to focus on how we can use these models in the context of inverse reinforcement learning. The underlying assumption behind inverse reinforcement learning is that the decision maker tries to optimize a cost function that is unknown. And then the goal is to infer such a cost function from observed actions of the decision maker. As an example, think of a lane weaving scenario where a robot is trying to infer the cost function that a human is using in order to make his actions. Now, the prevalent modeling assumption made by existing inverse reinforcement learning algorithms is that humans take actions by minimizing the expected value of a cost, meaning that humans are risk neutral. But a number of results, for example, from economics, suggest that humans behave in a manner that is inconsistent with a risk neutral framework. And indeed, humans are risk averse. In particular, they are averse toward ambiguity in the underlying uncertainty. This is an aspect that is well captured by coherent risk models. Hence, what I advocate is to consider inverse reinforcement learning models whereby we swap the expectation with a coherent risk measure. Leveraging the representation theorem for coherent risk measures, we have designed, to our knowledge, the first risk-sensitive inverse reinforcement learning algorithm. We're given demonstration from a human. We're able to conservatively approximate or estimate his or her risk posture by providing an outer approximation of the risk envelope of a coherent risk measure. Remarkably, this procedure can be done by solving a linear problem. Here I'm showing a result of a game whereby the red car is controlled by a computer and the green car is controlled by a human. This is an example of a trace of, let's see here, of an optimistic student in my lab, where the student always stays close to the car, even though the robotic car from time to time makes erratic decision. And this is a risk-averse student in my lab, where you can see how the student backs off substantially when he knows that the red car is about to enact an erratic maneuver. And interestingly, this behavior is well captured by our risk-sensitive inverse reinforcement learning algorithm. For example, here green is the realized trajectory by the human, and red is the trajectory predicted by our risk-sensitive inverse reinforcement learning algorithm. So you can see that at least from a qualitative standpoint, we're able to predict such a large back-off behavior. It's kind of interesting how in such a simple algorithm, a simple setup, we can see such a variety of attitudes toward risk. Finally, we're now deploying these algorithms on the game of fencing between a human and a quadrotor that showcases this aspect of inferring the intent and using that information to plan actions that anticipate possible reactions. And I will conclude by saying that risk-sensitive decision-making for robotics needs a sound theory that is compatible with the modern theory of risk. And in the context of robotics, the principal infusion of risk sensitivity provides several opportunities, both in terms of theoretical foundations, but also application to control, learning, and applications. Thank you.
Next up, we have Dorsa Sadik. Question for Marco while Dorsa sets up? Okay, I'm sure you get less shy as the day proceeds. Dorsa used to be at Berkeley, but this year she's faculty at Stanford. Welcome, Dorsa.
All right, okay. So hi everyone, I'm Dorsa Sadik, and I just started actually at Stanford in the computer science and electrical engineering departments. And my research is in designing algorithms for autonomous systems that safely and reliably interact with people and collaborate with people. So as autonomous systems and robots are leaving the factory floors and coming into our everyday lives, we have many examples of these systems. For example, in service robotics, we see robots coming into our everyday homes, controlling drones from the ground, or robotic surgery, or during my PhD, I worked on autonomous and semi-autonomous driving as one of these systems that actually interacts with people and needs to be safe. So I know all these systems are quite different from each other. They're very complex too, and there are many problems in each one of these applications. But one major thing that they have in common is they're all safety critical, and they need to interact with people. So when we are designing algorithms for these systems, we need to take into account these two major components of them. So when we think about safe and interactive autonomy, the problems that exist in safe and interactive autonomy, they really lie at the intersection of a bunch of different fields. Well, at the end of the day, we want to control our robots, so we care about learning and control. In addition to that, we need to have computational models of humans, so we care about human-robot interaction. And to talk about safety, formal methods is one way that allows us to be able to give guarantees about some of these systems. So in general, I'm interested in kind of pushing the boundaries of these safe and interactive algorithms for autonomous systems, and moving forward, I'm looking at team settings, so collaboration in team settings. And one of the first projects that we have started looking at is collaborative control in sequential decision-making tasks, for example, multi-arm bandit problems. So my student Sharon will be giving a lightning talk about this, and she'll be at the poster session. And we're basically looking at human-human collaboration. How can we model humans in these situations, or human-robot collaboration? So as I said, I started at Stanford 2 months ago, so everything is still shaky. So this is the lab. This is the Stanford robotics lab. This is my lab. It's not a conference room, it's a lab. So you can use your imagination, and what we're going to do is we're going to put a bunch of robots in the lab and create a home setting and look at these collaborative algorithms. So this is a picture from a couple of weeks ago. This is a picture from last week. Our robot arrived. So we're currently looking at actually setting this up and trying to design some of our algorithms on this robot. And currently, the main thing I'm working on is furniture shopping. So that is what makes me busy these days. So if it is not clear from the slides, let me make it explicit. I'm looking for graduate students in the fall of 2018. If any undergrads in the group, come and talk to me if you're interested in any of these. All right. So let's go back to this picture. So when we think about safe and interactive autonomy, kind of one of the main questions that's interesting is coming up with reliable models of humans. We really depend on having good models of humans. And I'm going to, in the rest of this talk, I'm going to focus on a specific project that I did when I was at Berkeley. This is actually work with Anka, Shankar, and Sanjit, where we were using active learning to model humans better. All right. So if you think about it, different people have different preferences about how any given robot should act. If we could get demonstrations of what people want, we'd be able to learn a reward function that captures their preferences. But the problem is acquiring demonstrations is sometimes quite challenging. For example, people have a hard time demonstrating trajectories for robots with more than a few degrees of freedom. And also, people can't always do the task the way they want the robot to do it. For instance, it turns out for driving situations, people don't want cars to drive as aggressively as them. They're actually more defensive than how they drive. So this makes the problem really difficult because driving demonstrations are not even informative of people's preferences. So we started looking at this problem, and we decided to, instead of demonstrations, leverage human comparisons. So comparisons, as opposed to demonstrations, can also give us information about the desired robot reward function. So instead, we decided to leverage comparisons, and what I mean by that is, let's say that we have a scenario, and in this case, the robot decides to show us two situations, two trajectories, in the same exact scenario. And then you would ask the user, well, which trajectory do you like better? Which trajectory would you take? And the human's response to these demonstrations gives us information about the robot reward function. So let's imagine that this reward function is a linear combination of a set of features, W times phi. And what the robot is really asking the human is, which one do you prefer better? Do you like W dot phi A or W dot phi B? Where phi A and phi B here are the feature counts for the two trajectories that it's showing. Okay? So we can take the difference between phi A and phi B. Let's call that phi. Phi here is a feature vector. And this feature vector induces a hyperplane in the space of all W's, in the space of all reward functions that we are thinking. So more explicitly, let's imagine our W lies in a three-dimensional space. Since we only care about the sign of W, we can assume that these W's lie in a unit ball. We can sample from this unit ball using the Metropolis Markov chain method. And then every query that we ask the user, every question that we ask the user, generates a separating hyperplane in this space. And the human's response to every query tells us which side of the hyperplane is preferred. Do you like this side better or the other side better? We also assume our humans are noisy because they're not going to exactly tell us which side is best for every query. So what we do is we don't completely remove the other side. We reweight the weights of this distribution. So what we do is we actually reduce the weights of the wrong side of the hyperplane. And we look at this new distribution. So to do this reweighing, we need to have some sort of an update function. And we actually choose a log concave update function. Any of these two functions would work in this case. And the reason we do that is at the end of the day, I want to be able to sample from my distribution. I want to find the maximizer of my distribution. And we can use the log concavity in this case. And we want to maintain the log concavity. And that's why we end up using a log concave update function. So let's go back to this picture. So as I said, well, every query is going to generate a hyperplane in this situation. And then some of these hyperplanes are going to result in just honing in on just the right information we care about. And others give us no information at all. So if you think about it, in this scenario, which queries we are asking the user matters, and we need to actively select them to gain as much information as we can in these scenarios. So that's all good. But if we look at these scenarios that we have, actually the state space that you're looking at is is high dimensional and is continuous. So I need to decide on the initial state of all the cars. I need to decide on my own actions. And I also need to decide on the actions of every other vehicle that's in the environment for two different scenarios. So that's quite high dimensional. Everything is continuous here too. So the problem is we can't really just rely on a discrete set of queries and take the best out of that discrete set of queries. Instead, our key insight here was to try to synthesize these queries directly from the continuous space and just from scratch. So instead of just discretizing the world, we are trying to solve an optimization where we are synthesizing each one of the queries. More specifically, we set up this problem as this optimization right here. We're assuming that I have an update function, again, that log concave update function, which was nice. The problem we are trying to solve is we're trying to maximize the minimum volume removed, subject to there being a physically realizable query. So these features should correspond to physically realizable trajectories that would work in the real world. So if you look at this problem, this is a maximum volume removal problem. It's a submodular optimization, and even if we use greedy methods, we have some nice convergence results in this situation. So in this case, we decided to use quasi-Newton methods to solve this particular optimization. And looking at our results, we see that, well, our algorithm converges much faster than non-active methods. It also converges faster than methods that do not synthesize queries. And after that, we decided to actually try our algorithm for a driving example. So with the user study, we brought in users to do this query-based approach. And in doing so, what we realized was that the users, the reward function of the users converged to similar and reasonable weights, as you can see the convergence results here. And these are all for 5 different features for the driving scenario that we did. And then after that, what we decided to do was we decided to compare this reward function that we have learned with other types of reward functions. So we perturbed our reward function with various amounts, and we decided to compare these in the user study setting. And what we saw was that our users significantly preferred the reward function that was learned by our algorithm versus these other reward functions. All right, so just to summarize, the key idea here was that we wanted to leverage comparisons instead of demonstrations to learn humans' preferences. And the way we do this is that we are using active synthesis to find these preferences in order to quickly converge to the particular reward function that we care about. And we have some nice convergence, theoretical convergence guarantees for the algorithm. Thank you. Okay.
A quick question for Dorsa while Claire sets up. Gotcha. Our next speaker is Claire Tomlin from UC Berkeley.
So So thank you to Anka and Marco and Ron for organizing this. It's a pleasure to give a talk. I'm going to talk today about a tool that we've been developing for now about 2 decades in my research group, which is reachable sets and reachability. And our recent work in this, really thinking about how we take this tool, which is really a tool from formal methods for verification of safety and for synthesis of safe controllers, and using it in real time. Okay, so this is kind of the perspective that we've been working on for years, which is that we've been very interested in safety critical systems, and we've been interested in developing tools for model checking. So tools that will allow you to verify the properties, the safety properties and the performance properties of a system. And the tool that we've been using is that of computing reachable sets. And the idea is fairly intuitive. If you have a representation of of your specification of the system, so say it's a safety specification, and in this figure, that red ellipse kind of stylistically represents all of the unsafe conditions. So unsafe situations, like in a group of vehicles, any 2 vehicles coming closer than a certain distance from each other, for example. So if you can take that specification and represent it as as a subset of the system state space, then theoretically, if you knew a model of the system up to some uncertainty, you could compute the set of states which could get into that region and then avoid that region. So we call that the backwards reachable set. And we're interested in control systems where we have some control authority. There may be authority in the system which is not under our control. So we consider those disturbances, and we've traditionally used a game theoretic framework of pitting control against disturbance and computing this reachable set, this backwards reachable set, the set of all states which, for all possible control inputs, a disturbance could push the system into this unsafe region. Okay, so that's been sort of historically what we've been doing. We have a set of tools, and they've been developed over the years, recently modernized, so please talk to us if you're interested in using these tools. So some recent advances in this, and this is something I talked about in a previous BARS meeting, is that of typically you're operating in an environment where you're gathering information about the system and how it interacts with the environment in real time. And so how do you incorporate that into reachability? And really this is a project that's been spearheaded by Jaime Fizak, who's here today, and Kene Akamatalu, who I think is coming this afternoon, and others in the group. But the idea is if you had a nominal model, perhaps a conservative model, then you could compute ahead of time the backwards reachable set of that system, and then as you collect data, you could update the control law as long as you operate within the safe region of operation. And after learning for a while, you may realize that you have a much better model of the disturbance in the system, and you can update that reachable set accordingly. And so we've developed a framework for doing that using a Bayesian prior on the understanding of what the disturbance model is, and then capturing that to become either more conservative if we underestimated the action of the disturbance, or less conservative if it is indeed a nominal conservative model. Okay, a second point, and this is something that's more recent that I'd like to focus the rest of this morning's talk on, is really now taking these reachable sets and using them in real time. In fact, using them for robotic path planning. So this is a project that we call Fast Track, for fast and safe tracking, spearheaded by Sylvia, Mo, that's the Stanford version of Mo now, David and Jaime. And Sylvia and David will both be giving lightning and poster presentations about their aspects of this work this morning. So the idea behind Fast Track is as follows. Let's sort of talk about the evolution. So on the left-hand side, we have slow and accurate planning. And so the idea behind that is, you have a safety critical system, you have a dynamic model, typically fairly high dimension. You want to plan with the system, you want to avoid collisions and other safety situations. And so if you could, you'd like to develop a planner for that high dimensional, or typically high dimensional model, but that's going to be slow and possibly or quite probably not implementable in real time. On the flip side, on the right-hand side, we have kind of what we do a lot of today, which is fast but less accurate planning. Just come up with a very simple, maybe point mass model of the system, and then plan based on that point mass model, and then use some kind of LQR control on your real dynamics to try to get your actual system to track your fast plan. And the problem is you don't have any guarantees about safety. Then you can't guarantee ahead of time that the plan is even dynamically implementable, or that your system won't collide with, say, obstacles in the environment. So the idea behind Fast Track is that you bring in a pre-computation which uses reachability to compute what we call a tracking error bound between a high-dimensional dynamic model and some kind of low-dimensional, say, point mass model that you use for fast planning. Okay, so you develop, the idea is quite intuitive. You develop a relative, an error dynamics model between the high-dimensional model, say a 10D model of a quadrotor dynamic, and that simple 2D point mass model or 3D point mass model. And so that represents the relative dynamics, and then you compute the reachable set based on that relative model to guarantee that the vehicle, that relative dynamics stays within a given bound. And then you just use that bound in fast planning. So you do the pre-computation ahead of time, and then you use that bound as basically the object that you're propagating through on the fast plan. And that's represented here. That tracking error bound is this sort of region around the point mass. So how do we compute this tracking error bound? It's essentially what I said. You basically form an error dynamics between your high-dimensional model and your low-dimensional model, and then you pre-compute a reachable set based on that. So, and you can do all sorts of neat things using reachability, right? You have control authority available, you can consider disturbances. So you can make it conservative by assuming that the planning system tries to maximize the cost, the tracking system tries to minimize the cost, and you can capture this maximum cost over time. So here's an example for just a 5D system tracking a 3D system. This is the computed error bound. And so what we're showing here are the level sets of this error bound for different values of a pre-computed tracking error. So these are dynamic systems, right? So these sets are typically non-intuitive to look at, but they're actually capturing the dynamics in this error bound. Okay, so this is for this system, what this tracking error bound looks like over time. And then how do we use this in real time? So the offline computation, that pre-computation is done once. You take the planning dynamics and the tracking dynamics, you perform the pre-computation, that gives you the value function from which you can get both the tracking error bound and via reachability, the control that keeps you inside the tracking error bound or keeps you inside that bound that you've computed. So that's done once ahead of time, and then you implement that in real time. So this is performed iteratively, but you only have to do the high-dimensional computation once. So here's an example of a 10-dimensional quadrotor, which is tracking a 3-dimensional point mass, and the planner that we're using is a simple RRT planner here. And so the tracking error bound is a 10, so the relative dynamics are going to be of dimension of the highest dimensional system. And what we're showing here is the projection of that 10-dimensional tracking error bound in the 3 position variables that are relevant in this simulation. Okay, so it's detecting those obstacles in real time and then using it to update its plan. Okay, and this is just a plot of the projections of those tracking error bounds. This is another example. This is a 5-dimensional system which is tracking a 3-dimensional system, and the planner used is a fast sweeping method. Okay, so again, we're showing the projection of that tracking error bound, and it's computing that plan now in real time. And so you have a guarantee. I mean, the key here is that you get an a priori guarantee on the dynamic feasibility and the tracking error, and you can use it to avoid collision with obstacles. So finally, let me conclude with the latest work, which is, this could be quite conservative because you're computing this bound and you have to, basically propagate this bound through space. Well, as we know, the more detailed the model in the planner, the less conservative it becomes. So what you can actually do is kind of fast and slow, or you could have different degradations of what it means to be fast or slow, and pre-compute that tracking error bound for a variety of different planners, low-dimensional planners or higher-dimensional planners, and then switch in real time. If you come to a corridor where you couldn't actually go through that corridor with the very fast planner, you can recognize that and switch to a slower planner that has a smaller tracking error bound that allows feasibility of that. And this is just shown in some simulations. We'll show you the actual experimental results in the poster session. But you see here we represent, in that blue corridor, we're switching between a fast planner kind of in wide open areas and then a little bit of a slower planner in the areas that are impacted by obstacles. Okay, thank you very much.
Our next speaker is Michael Kochenderfer from Stanford, Aeronautics and Astronautics.
All right, some of my earlier work back when I was at Lincoln Laboratory resulted in the development of the ACAS-X system. It's an aircraft collision avoidance system, and it's derived from a partially observable Markov decision process, or a POMDP formulation. And in 2013, we had the first flight test, and I would have to say that few things are more exciting than being on a large aircraft, flying directly at another large aircraft, and hoping that this POMDP business works out. And it did, and it's currently being standardized for use on every large transport aircraft in the world. And there's interest in developing a similar kind of system for unmanned aircraft. And the first flight test for that was in 2015. It was a major success, but it's still under development. And it also uses a POMDP formulation. So I won't go through all of the details, but for the ACAS-XU, U for unmanned aircraft formulation, there are a variety of different maneuvers. One is clear of conflict, weak left, strong left, weak right, and strong right. Has a variety of different state variables. In this initial formulation, we have 7 discretized state dimensions. The solution to this has 600 million state action variables. This requires 2.4 gigabytes of memory, but on our anticipated test aircraft, that has only 150 megabytes available. So we have to develop a compression scheme. We worked very hard to come up with a new compression scheme, but then we were tempted to just use neural networks. And I was hesitant to do this because back in, I think it was 2014 or so, I was briefing the Office of the Secretary of Defense on ACAS-X for manned aircraft. And there was no mention of neural networks in that talk because we don't use neural networks. We use a variation on approximate dynamic programming. And someone afterwards came up and said, I don't believe in this neural network stuff. Another reason why I'm hesitant is the idea of putting neural networks onto an aircraft fulfilling a safety critical functionality is a little bit scary. But we decided to give it a try and see what happens. This is the architecture that we used. We tried out a variety of different algorithms, different architectures, different numbers of hidden layers. Unfortunately, it turned out to be pretty tricky. You can't use the standard squared loss function because you need to not just accurately estimate the state action values, but you also really want to preserve the best looking action. And I can talk about those details offline. But eventually we got it to work and we got policy plots that look pretty sensible. So the top left plot shows where you would produce different advisories under the assumption that the other aircraft is flying directly at you. And on the top right, that's what happens when the aircraft is approaching perpendicularly. So on the top, that's the original table. On the bottom is what you get with the neural network, and you can see that the neural network kind of smooths things out. But the thing that was really surprising is that it actually worked a little bit better. So we ran simulations on 1.5 million encounters, and we got a performance increase, which is very strange, because normally when you regress something, you induce regression error. But here, since the neural network involves many fewer parameters, it actually induces some regularity and smooths things out. On the bottom left is a comparison between the original table and the neural network on the probability of NMAC, or a near midair collision. So there's actually a slight safety increase. And at the same time, it decreases the number of alerts. It also decreases the number of reversals. So a reversal is when you change the direction of the aircraft, and you really do want to try to minimize that for efficiency purposes. The memory required, the neural network is also shown on there, but it's so small you can't see it. But unfortunately, the runtime is really slow compared to the table lookups. With the table lookups, you can do direct memory accesses. But with the neural network, you have to do a full forward pass through this deep neural net. So we tried a whole bunch of different standard neural network compression techniques, and they were terrible and did not work at all. So one technique that we used that actually worked amazingly well was breaking up the state space and training separate independent neural networks. And that actually resolved the situation. We did get a small increase in the NMAC rate, as you can see on the table on the right. Still lower alert rate. Reversal split is when you go from alert to no alert to an alert. Brought down the memory required and the relative runtime performance. It's about the same, maybe about 7% faster with the neural net. But of course, we come back to, so that was all surprising and very exciting, but we come back to the question of, can we really trust a neural network to always work correctly in safety critical systems? And this led to some collaboration with my friend Clark Barrett, a professor in computer science, and his postdoc, Guy Katz. And this resulted in the ReLU-Plex algorithm, ReLU coming from rectified linear units and Plex from, it's kind of similar to the simplex algorithm. And we were able to prove safety properties about this deep neural network. I'll show you an example of a case where it found a counterexample that indicated that we needed to improve our neural net. So here's an example. There are a variety of different properties that you might want to be able to prove, and it takes on the order of about an hour or so to prove these various properties, but here's one. So this property is when the time to being co-altitude is maximal, so you're fairly separated in terms of altitude, then there shouldn't be any strong alerts. And visually, this looks true. This is a slice of the state space where you've already produced a weak alert. And visually, this looks true, but it turns out that the theorem prover was able to find a counterexample, and we can actually zoom in here, and it found this kind of weird artifact from the neural net. And so we had to address that. So I think I'm at time. So I run the Stanford Intelligent Systems Laboratory. This is the contact information, and we're looking for good postdocs. So we needed to use flight certified hardware, so without GPUs. And we were basically at the runtime budget with the table lookup. So we really had to hit that metric.
Okay, our next speaker is Anka Dragan.
Thank you. Hi again. So we've been getting these robots to be better at optimizing their reward functions. And with that comes a stronger burden on us, the people designing these reward functions, to make sure that we design the right reward functions. It turns out we're not so good at that sometimes. I love this blog post from OpenAI that details their struggles with this. And they give this fabulous example of an agent playing a boat racing game. So here's the agent, and this is the trained policy that it comes up with. The reward was to optimize score in the game. And what it does is it figures out this loop it can make where it conveniently collects these turbo thingies. I don't know what they are, but they give you hell a ton of points, is my understanding. So all the other agents are kind of happily actually racing in this boat racing game, but you know, this is what this thing thinks is optimal. And this is not a new problem in any way. So Stuart and Peter gave this other example in their AI book of a vacuum cleaner. So for those of you who don't know that, imagine that you design a robot vacuum cleaner and you reward it for the amount of dust it manages to suck in from your floor, right? So the more dust, the better. And then the optimal policy is to go and suck in some dust and then dump it all back on the floor so that you can suck it back in again and dump it back on the floor and repeat. So I think these examples are illustrative of the fact that we're not so great at designing these reward or utility functions for our robots. And that can lead to poor consequences at deployment time, at test time. And so one thing that we've been looking at lately is how might we be able to alleviate these bad consequences? And to me, the problem really starts with the fact that we define robotics in isolation, right? You have a robot, it takes actions to optimize some sort of utility function that is exogenously specified. But the thing is, it's not actually exogenously specified. It's specified by a person. That person comes up with something, we're going to call this the proxy reward, theta tilde. And what we currently do is we just stick that into the robot's objective and have the robot optimize that. This is the current pipeline. Our idea is that, given that we know that oftentimes theta proxy is not what we actually want, is not the correct objective, let's maybe not do that. And so there certainly is a lot of information about what the correct objective actually is in this theta proxy, but maybe not all of the information. And to wrap our heads around this, we look back at this boat racing game. So here it is simplified into a toy example. Imagine that what happened with the boat is that it could have won with a high score, let's say 20. But instead it chose to not win, but get an even higher score, let's say 50. Now, why did it do that? Well, because the designer of the system decided to specify score as the reward. So far, so good, but why did the designer of the system decide to specify score as the reward? And here we make an assumption that when people design these reward functions, they do a fairly good job. They don't just write it down and ship it off and deploy the robot, that they probably try it out on some what we call training environments and make sure that it works. So if that's true, then clearly the training environments must have looked very different from the actual deployment, the test environment. In particular, in these training environments, it must have been the case that the options look more like you could win with a high score versus lose with a low score. And so score and winning were correlated at training time, and the problem was that they stopped being correlated at test time. And so that led to our insight in this work that instead of taking the specified reward as given for granted, we should only be assuming that it did well in the training environments. That's really what we know. So this is work by Dylan and Smitha in collaboration with Peter and Stuart Russell. And the way we mathematically achieve this is by treating the specified reward, the proxy reward, merely as an observation about the true reward conditioned on the training environment that we know it worked well in. So We assume that the person is roughly solving a reward design problem when they specify the reward. There's some true reward function that they kind of implicitly know, but when they try to explicate that, they end up with something that's not quite the same necessarily. Maybe there's some missing parts over there. And so how might we come up with that something that's slightly different? Well, here to model this, we assume that people can look at these training environments and figure out how the robot will behave given a particular specified reward in those training environments. For instance, the robot might behave approximately optimally. So now they can actually evaluate how good that behavior is with respect to this internal actual reward function. So that doesn't mean you can explicate the reward. That just means when you see behavior, you can figure out, yeah, that's what I want, that's good. And then the reward designer is essentially trying to solve this problem of finding a reward to specify that ends up with the robot, when behaving in a training environment, doing as well as possible with respect to the true reward. And what we do here is we assume that the person is approximately optimal at solving this. So for a particular proxy reward, theta tilde is likely if it leads to true reward and expectation over the behaviors that the robot will execute in the training environment given this proxy reward. And beta here is just the rationality coefficient. So this is our model of how we designers might actually be specifying these reward functions. And what we do with this model is we invert it into something we call inverse reward design. We have the robot take this proxy, interpret it as an observation about the correct reward function, and apply Bayesian inference to come up with a posterior distribution over what the true reward function might actually be. So let me try to untangle why this works by looking back at this little boat example. So here imagine that the robot is considering this hypothesis space of many, many different possible reward functions. There's score, which is the thing that the person actually specified. Maybe there's winning, losing, negative score, a bunch of other things, right? So what's interesting here is that if you look at winning and score, they lead to the same behavior in the training environment. They lead to the robot winning with a high score. But so this is kind of what enables the robot to figure out that if what you actually meant was to win, that's what you want. Score is a pretty likely reward to actually specify because score, when you optimize it, it leads to winning, and winning has high reward with respect to the winning reward function, so that's nice. This also enables the robot to figure out that score is kind of unlikely to be specified if what the person actually wants is for the robot to lose. Again, because score leads to the winning reward, the winning behavior. The winning behavior is not high reward when you actually want to be losing. And so when you do inverse reward design, you end up with this probability distribution where the robot assigns high probability to winning and score, not so high probability to losing. So what's cool about this is that the robot, you specified score, the robot trusts that you didn't mean lose, but it doesn't trust that you didn't actually mean win. And that's the key to making this work. Now, this is all nice and good because we have an awesome feature there, winning. We just have access to that. But in reality, robots don't get these important features in these tasks just handed out to them on a silver platter. So to test what happens in those sort of scenarios, what we did is we made up this 2D navigation scene where there's these different terrain types that the robot has to go through. There's a target, there's grass, there's dirt. And then only at test time, we introduced a novel kind of terrain. For a dramatic effect, we'll call this lava. And the catch here is that the robot doesn't actually get to see these latent terrain, these terrain types. They're actually latent in the space. All the robot gets to see is these observations, these raw observations about them. So they're at train type, there is no lava, and what happens is that the person wants to specify some reward function that gets the robot to reach the target, maybe avoid the grass, go over dirt, stuff like that. So what they might do, for instance, is they might make up classifiers based on the raw features for these things and define some sort of proxy reward function based on that, totally forgetting that lava is a thing that they should be worried about. At test time, there is lava, and what we see happen is that when you optimize the proxy specified, it oftentimes gets the robot to actually go over lava because there's nothing really in the reward function, the proxy reward function, to penalize lava necessarily. with inverse reward design, what happens is the robot reasons about this training environment and reasons about the fact that, well, about which other possible reward functions would have led to similar behavior, essentially, in this training environment. And we find that it fairly consistently avoids lava. It does so across all sorts of different ways of specifying the reward and different test and training instances. And so what seems to be happening here is that the robot figures out that it doesn't really know whether lava is good or bad without actually knowing explicitly what lava is, and before even encountering lava, because it does this based on the training environment. So I thought that was really, really interesting. We're starting to look at this in the context of motion planning, so more realistic, non-2D navigation problems, and we're finding similar results. And to wrap up, this is kind of an instance in this agenda we've been pursuing lately to look at human guidance and treat it as observations about what people actually want these robots to be doing. Thank you.
This concludes the first session of faculty talks. Now we're going to have a rapid fire of spotlight talks.